Want to see this thing shoot 200 darts in a second? Okay, technically that wasn't 200 darts in a second, but it was still pretty fast. So why'd I make it? Well, Nerf blasters with very high rates of fire are very satisfying. The fastest one you can buy is the Pew Pew from PewTech. The fastest ones ever built are by 3D Printed Life and Gatling Tommy. Both can shoot up to 100 darts per second, but I wanted to go faster. Let's start from the beginning. I first needed to understand why 100 darts per second seemed to be the speed limit. To start, I looked at the slow motion clip of the Pew Pew. Let's break down what's happening by tracking what I'll call the firing time and loading time. Firing time being the time the dart is in contact with the flywheels, and loading time as all of the events required to get the next dart into the flywheels. The cycle starts with the solenoid extending to push the dart into the flywheels, the dart getting shot through the flywheels, and the next dart moving into position for the next cycle. Even with the very well-timed solenoid, the majority of the cycle time is wasted waiting for the next dart to get into position. The magazine spring and solenoid are moving just about as fast as they can, so the firing rate is capped at around 50 darts per second. 3D Printed Life reduced the loading time enough to achieve 100 darts per second. The slow, spring-loaded magazine and solenoid were replaced with a fast rotating drum of darts. Here's a simplified recreation of the design. As the magazine moves towards the two belts, each dart is pushed out and then pulled through the belts. As the magazine moves faster, the firing rate increases. If the belts can't pull the dart out quick enough, the movement of the magazine will jam the dart up against the rest of the blaster. Unless the darts are pulled out quicker, the blaster won't be able to go much faster than 100 darts per second. Every blaster I've seen, whether magazine, belt, or drum fed, store and feed darts in the same manner. Darts are stacked like this, moved into position, and then fed into the firing mechanism. Any design like this will always have some unavoidable amount of loading time. So would it be possible to stack darts in a different way to get rid of that loading time completely? If the darts are lined up end to end and all pushed towards the flywheels as one group, that loading time is pretty much eliminated. The slow motion shows that there is still some loading time, but all it takes to decrease that is to push the line faster. Alright, with that basic concept in mind, I had two goals for this project. I wanted to have a magazine capacity of 200 darts and reach a firing rate of 200 darts per second. So what does a 200 dart capacity magazine look like with the darts stacked end to end? I could try and lay each of the 200 darts end to end in a straight line, but that's close to 25 feet. This right here is only 1/3 of that. My next thought was to break the long line of darts into shorter segments. This way I get short bursts at a very fast rate, but there would still be the problem of the loading time bringing down the average firing rate. How about I put all the darts in a coiled up tube and blow them out with air? It doesn't quite work, but it does make a goofy sound. Let's take a look at a nut, bolt, and a piece of string. Let's pretend that this blue string is a bunch of darts laid end to end and wrap it inside of the threads of the bolt. All it takes to shoot them out is to turn the bolt. Now that's an idea that could work. Let's start with a drum that is about 7 inches in diameter. Add a nice cutout and then fill it with darts. Unfortunately, I couldn't fit any more than 50. Next, I'll add a thread to the drum and add a roller that will act as a nut. These two threads at the top and bottom are complete circles, which will give the drum time to accelerate and decelerate before the roller engages with the thread. Next is the central shaft and some structure for it. Now for the base plate, dart transition, and flywheels. As the drum threads down, the darts will go into the transition piece, separate from the drum, and then go into the flywheels. I'll add these 2 extra shafts to drive the rotation of the dart drum and some springs here and here to push the drum into the thread roller and force it to catch on the thread. And last but not least, a clear shell that spins with the dart drum to keep the darts in place. Big thanks to my bud Chase for helping me brainstorm some of these ideas. You get a gold star. Before I start building this thing, I need to figure out how fast it needs to spin to reach a rate of 200 darts per second. An entire line of 200 darts is about 23.6 feet long and will need to travel past a single point in 1 second. This works out to be 16.1 miles per hour. For the darts in this drum to reach that speed, the drum will need to spin at 755 RPM, which doesn't sound too crazy. To put that into perspective, a 24-inch ceiling fan spins at around 500 RPM, and the max speed of a washing machine is around 1200 RPM. I'll be using this beast of a motor to spin the drum. It's a NEMA 34 stepper motor used in industrial robotics applications, and it just so happened to be the only motor I had laying around that was large enough for this project. The next largest motor I had was this thing. Alright, it's building time. Before adding a motor, I spun the dart drum by hand. The first few darts ejected perfectly, but the rest quickly jammed and caused issues. I did another test with less darts and noticed that the darts jammed against the transition piece. I figured that the large gap between the drum and the shell let this happen, so I made a smaller shell and tested it. The second shell was too tight on the darts, so the drum couldn't move down the shaft. The third shell was in between the first and second, but it still didn't work. The darts wanted to roll over this barrier when the drum moved down. Not ideal. I had to change the drum to fully encapsulate the darts, which unfortunately meant I had to remake a few parts. Once assembled again, I decided to test the motor at speed. It got above the goal of 755 RPM before stalling at around 800. Then I tested the threading roller to see how well that worked. Not bad at all. I then tested with darts again, hoping that the centrifugal force would be enough to get the darts to come out. Unfortunately, the less than perfectly smooth drum held onto some of the darts. To fix this, I added a wire that would run along the drum and guide the darts out. I tested the idea manually and then with the motor with some good results. The big issue with using a wire was at the top and bottom of the drum. The wire would ride in the thread and get knocked off course. I took the wire out and thoroughly sanded the drum to hopefully prevent the darts from getting stuck. At a 50 dart per second rate, it worked pretty well. At 100 darts per second, it did not. Taking a closer look in the barrel, it became obvious that I still needed something to guide the darts out. Instead of a wire, I cut up a tape measure. The tape can hold its shape very well, is flexible, and doesn't ride in the smaller thread. I did some more tests at higher speeds and was still having some issues. Turns out the thread roller would flex a ton and cause the drum and darts to misalign from the barrel. I cut a new part out of steel and replaced the old one. I tried another test at the 100 dart per second rate, but it jammed pretty quickly and stalled the motor. There wasn't an obvious cause for this jam, so I spun the motor up at a slower speed and it pushed the rest of the darts out. This meant that the jam was caused by excess friction. Most of the friction was from the darts rubbing up against this transition piece. I designed a new part and used a bunch of rollers instead. It reduced the friction by quite a bit. The first 100 dart per second test jammed immediately for some reason, but the second test went pretty well. The drum slowed down halfway through because the belt was slipping. I tensioned the belt and gave it another go. The sudden thread engagement made me jump a little, but I did manage to get the rate of 100 darts per second. I did another test just for fun. I upped the speed to reach a rate of 160 darts per second, but the drum thread didn't want to engage with the roller. These higher speeds were making me a bit nervous with how sketchy the whole setup was, so I decided to make a handle. Now the whole thing is much easier to handle. The next set of tests at 150 darts per second presented some other issues. The thread roller would disengage from the thread and cause the darts to misalign from the barrel and jam. This was partially due to the large amount of runout the drum had. Instead of adjusting parts to reduce the runout, I made some more parts out of steel. The end result was this beefy, spring-loaded roller. It follows the drum quite nicely. I tested again at 150 darts per second and didn't have much luck getting the thread to engage. It took a bit of pulling back on the spring roller here to hopefully make the thing thread. It jammed after 8 darts. It was getting increasingly more difficult to get the drum threads to engage with the roller. After taking a closer look at the drum, I saw that this starting thread was getting flattened. This edge should be sharp. This drum is a 24-hour print and takes a couple of hours to clean the support material out, so I didn't want to remake it. Instead, I experimented with angling the roller to get engagement. Big thanks to my other bud Cole for this idea. You also get a gold star. The idea was very promising, so I made a plastic prototype. The roller moves back and forth and can be angled with this servo. The old one mounted to the plastic base plate, which was way too flexible, so I made it mount to the aluminum standoff instead. It worked pretty well at slow speeds. Once I knew that tilting the roller would work, I made it all from steel. I tested it at some higher speeds. I reassembled the whole thing and did a test at 100 darts per second. It jammed because this last dart got caught in the tape measure ramp. The next test at 150 darts per second stalled the motor halfway through. No darts jammed, so the motor was able to push out the rest of the darts at a slower speed. This was also caused by excess friction. I couldn't think of any quick and easy ways to reduce friction again, so I decided to focus on optimizing the pulley ratio to maximize torque. Here I've got two pulleys connected by a belt. Since both pulleys are the same size, this would be called a 1-to-1 ratio, which is currently what my setup is. Speed and torque will be the same on the motor side as well as the driven side. If the driven pulley is twice as large as the motor pulley, it becomes a 1-to-2 ratio. The speed on the driven side is halved, but the torque is doubled. Switching the two pulleys will turn this into a 2-to-1 ratio where the speed on the driven side is doubled, but the torque is halved. This is the torque speed chart for my stepper motor. It graphs the torque it can produce throughout its entire speed range. The most torque it can produce is between 0 and 300 RPM, and it's been stalling at around 550. I'm hoping it will be possible to mess with different pulley ratios to get the motor spinning at these slower speeds to maximize torque on the dart drum. I pulled the data from the chart into Excel and added these columns to calculate how much torque will be applied to the drum given different pulley ratios. I also switched the graph to plot the torque at the drum instead of the motor, and converted the RPM to darts per second. I focused on the 100 to 150 dart per second range, and started messing around with different pulley ratios. I ended up settling on a 1 to 0.775 motor to drum ratio. Compared to the 1-to-1 ratio, it has a bit less torque at the 100 dart per second mark, but it has a bit more at the 150 mark that the motor has been stalling at. I put the new pulleys on and did a test at 100 darts per second. It got halfway through before stalling. I did another test again with the same result. Apparently that little bit of torque difference was important. I switched back to the original pulleys, and for whatever reason it also stalled. I zoomed out on the torque chart and realized that the difference between the two ratios was more or less the same at these speeds. While it was worth a shot. It seemed like this motor needed just a little bit more torque, but I didn't have any stronger motors laying around.
But you know what will work? A parent's e-bike.
I wouldn't exactly call this bike portable, and all I really need is a motor, so I'm gonna cut it out. Hey Dad, what's up?
You better not be messing with my bike.
I'm gonna have to call you back. Guess it's plan B. I ended up building a set of rollers that the rear tire of the bike will sit on. My first test was of course the baseline of 100 darts per second. 2 drive rods twisted and prevented the drum from moving down. I tightened the shaft collars and decided I should do some dry fire tests first. That last test destroyed the roller and damaged the thread on the dart drum some more. Whoops. I replaced the roller and did another 100 dart per second test. The drum stopped moving down because the roller ended up disengaging from the thread. I did another 100 dart per second test that was slightly more successful. It was the same issue as before. I noticed that the roller wasn't moving back and forth as easily as it should have, so I replaced this bushing with a longer one. I suppose it moves better? I was really grasping at straws at this point. I decided to give it one last test at 150 darts per second before moving on. It was very clear how much of an impact that damaged thread was having on thread engagement. This time, the roller engagement was even worse. So I didn't exactly reach my goal of 200 darts per second, but I'm getting there. I still need to find a higher torque motor and figure out how to prevent the threads from disengaging. I've already got plans for solving both of those issues, so stay on the lookout for that. Thanks for watching.